Hello everyone, today we're going to be talking about the stochastic integral, and I usually do videos in Italian, but I looked up on YouTube, and most of the theory on stochastic integrals is, at least as far as these I found are concerned, is about stochastic integration, stochastic calculus applied to finance, which is something that interests me, but I haven't really found a deeper theory, a mathematical theory on what's behind the stochastic integral. So I figured I might as well do it. And FYI, I usually do this video to prepare myself for exams. I'm a master's student here in Italy in mathematics. So yeah, let's waste no time and let's dive into it. So what we're going to be taking a look at today is stochastic integrals. So the definition, which the way I've seen it, and my professor refers to a book which I've forgotten, but it's a great book. We're going to be looking at, so it's not a definition, it's seen as a theorem. So we're going to be proving some propositions for martingales bounded in L2. So what we can do is already spoiled. Eventually, this is the object, which is a random variable. If you fix t, otherwise it's a stochastic process. So the stochastic integral is a stochastic process. So that we're gonna be defining in today's video this dude. So it's might be a long video because I also, to some degree, we'll take a look at some of the proofs that of the things the properties we're gonna be mentioning, as a, let's say, somehow decent mathematician should do. So I'll try to leave timestamps. So let's dive into it. What do we need? So the spaces we're gonna be working with, are, and what we so as far as we have some sort of a martingale, which we'll be talking about, and a process. So what type of process do we need? So let's talk about the martingale first. As we mentioned, we want martingales bounded in L2. So we're going to be calling this H space right here the space of M martingales. So yeah, I'm gonna be giving a lot of things for granted in this video. If you do have any questions, just let me know in the comments, and I'll try to actually go review some concept if I remember. But yeah, we're gonna be giving a lot of things for granted here, assuming that you do have a basis on stochastic processes. So basically what I'm saying is you do know what a martingale is. M is a martingale bounded in L2, so such that supremum of the expectation of the martingale squared is finite, bounded in L2. And what is H? H is going to be living in what we will be calling, now I'm not sure this is standard notation, that's the way I've been taught, so that's the way I'm telling you guys, but it's just notation, then you can call it whatever you want. So for every M in H2, so every bounded martingale in L2, L2M is a set of H progressive, and I'll say what progressive means in just a second, such that here we need some bounds. So the expectation, which is eventually going to be the L2 norm in this space, which we're talking about, lots of things to say as usual. 0, infinity, you can also go up to t if you want, of what? Of the process against the quadratic variation, which is finite. So I hope and I believe there's not much to talk about this space H2, whereas I think process progressive means that it's ft you can call it, this is the Borel sigma algebra of time, so up to time t if you want, if you fix s times ft measurable. Okay, so if it requires satisfies this measurability condition, and one thing that it's actually extremely useful is that there's a bit of a remark. Okay, I'll type it as a memo. I like memos. Adapted. So if a process is adapted and continuous, by continuous I will always refer to the its trajectories, then it's progressive. Okay, that is going to come in very handy throughout. I mean, it has come very handy throughout my lectures, but I think it's actually extremely useful. So I'll leave it there. What is the correct variation? So the definition is for a, I think you can define it for a local martingale. For a martingale, so M is martingale, correct variation is defined as the limit of the Riemann sums, basically, of, I'm gonna define everything I'm writing right now, no worries. So what you do is, so that it's the quadratic variation, right, up to time t. Excuse my handwriting. Here we're integrating against it. Okay, so what you do is you take an interval 0t, you take an increasing sequence of partitions, which we're going to be calling throughout the videos on stochastic integration pi n. So this is an increasing sequence of partitions of 0t. Then what you do is you take the limit of, excuse my handwriting, uv in pi n. So you take the limit of a sum. These are the Riemann sums, excuse me. And this is the difference. So delta muv basically means mv minus mu, and you square it. That is the quadratic variation. Okay, and this is not a stochastic. This is actually a very interesting remark. So that's what I said about I haven't found any of these concepts. I haven't really found on YouTube, probably because they're not really sought after. Its implications more interesting probably, but I think it's, as a mathematician, you should probably know these. So this is not a stochastic integral. This is a Lebesgue-Stieltjes integral, because this is an increasing process. So everything here is well defined as a Lebesgue-Stieltjes integral. You don't need stochastic calculus. Okay, that's just an observation. So with that in mind, what we can do is we can start. I'll leave this here. So let me do a cloud. Huh. That's us thinking. So excuse me. Humor of the mathematician, or spare mathematician. So what we can do is you can define an elementary process. So as usual, you take a partition of time, okay, and you define as you would any elementary, step function. Basically, here we just have a process plus 1, okay, of s. And what you can do, so I'm gonna be, from now on, I'm gonna call this, this is the space of elementary process, and this also is going to be extremely, we'll get back to this, because, okay, I'll just spoil it for you guys. This is a subspace of L2M. So with that information, you already know where we're going. Okay, we're going to be using elementary process to then use and then go on to an argument density, which is, how the Ito, which the stochastic integral is also called Ito integral, it's eventually defined, because you need to prove the limit exists of what? Of this. So you integrate h, which h is in L to M, remember? And you use the elementary process. You use hi, and then again it's the usual partition. So basically we are partitioning T1 up to TP. Okay, partition of 0T. Okay, and that's again notation. I'll explain it. That is the notation for the stop martingale. Okay, up to time t. So that's the infimum. This is notation for the infimum. Okay, sometimes you write this. Sometimes you can write it like this. Just notation. Means to stop the martingale. So this you can also write it using this notation right here. This would be m ti plus 1 stopped. Okay, same notation. So this would be the integral of the elementary process. Excuse me. Eventually, the argument is we work by density. This density, this is a Hilbert space, and you can prove this is a subspace. So eventually the L2 limit exists. You need to prove the existence of a limit. How do you do it? Cauchy sequence in Hilbert spaces. Then you know if you have a Cauchy sequence, the limit exists. That's why we need functional analysis. That's where the magic of measure theory, functional analysis are mixed up, and that's called probability theory. But what are the so let's write theorem. What we know is theorem slash definition of stochastic integral slash integral. So also, I should have mentioned that earlier, but clearly, so I'm defining this for martingales bounded in L2. I'm sure you guys know a very famous and well-known process, which is a martingale bounded in L2, which is usually written like this, right? So the Brownian motion is a martingale bounded in L2. The quadratic variation of the Brownian motions is bounded, right? It's time. It's variance. Yes. But also, there's so much to talk about, really. It could go on for hours. We're doing for martingales bounded in L2. Once we done this, I should have said that earlier. It's always like this. Once you, okay, let's see now. Once we can, right now basically what we're going to do is we're going to prove that, okay, I'll just state it. The integral is in H2, so the integral is a martingale bounded in L2. Okay? Then this map here that takes H in L2M, okay, and goes into H2, extends to an isometry. So what does it mean? Reminder, what's an isometry? It's a linear map that preserves the norm. So the norm of HM in H2 is equal to the norm of H in L2M. Okay, does the norm exist? Yes. It's induced by a scalar product. Why? Because they're Hilbert spaces, as we just mentioned. 3. And what's 3? 3 is that you have uniqueness. So HM is the unique process. such that for every other martingale bundle on 2, and what you have is integrating. So we talked about the quadratic variation, right? We defined it. We just technically it's a reminder because I'm saying you already know this. So integrating, so this would be the covariation, okay? Because you don't have the same process. So usually when you have the same process, it's called quadratic variation. Otherwise, it's called covariation, okay? It's defined the same way. Here you would have the increments squared. Here you have the product of the increments, okay? The limit of this over partitions, blah, blah, blah. It's the same thing, you just, okay. I see you nodding from the screen. So, so integrate, doing this, it's the same as integrating h against the covariation, okay? So we're going to be showing that. Last but not least, stopping the integral. So for every t stopping time, which also it's extremely important concept in stochastic processes. So I'm assuming you already know what a stopping time is. Usually it's done at the later stages of your probability theory courses, right? When you start talking about when you start talking about stochastic process, we usually first stochastic process you talk about are Markov processes. So very stopping time, stopping the integral. Okay. Now every time I use this dot, sorry, I forgot to mention it. I'm referring to the integral, okay? So it's not a scalar product, as sometimes usually referred to in standard notation. H, every time I say h dot, I mean, not necessarily h and m, but when I use this dot, I mean the integral of h against m, okay? Sorry, forgot to mention it. So, again, stopping the integral is the same as stopping the martingale, which you can also write like this. Those are all equals, okay? All right, so now that we said that, what we're gonna do is, it's very interesting. So, what we just did is, for the cap, we defined, kind of, we haven't really stochastic integrals for bounded martingales and L2. So we defined the two spaces we're going to be working with. So our integrants and integrator spaces. Excuse me. What we did is first by using elementary processes. Okay. We said, okay, it works for elementary processes. Can we make it work for any L2 process? And the answer is yes, because you can prove it, okay, by the definition that the set, the space of elementary processes is actually a subspace, a dense subspace. Okay, dense is very important of L2M. Okay, so that's a key. This is very important. We're not going to prove it. It's pretty long, but it's tedious, so it's not really complicated. And then we listed the properties of the stochastic integral. Okay, which we're going to be 20 minutes. Yeah, who cares? We'll prove it. At least I'll give you some ideas of the proofs. Now, eventually, what you can do, and I don't think I'm going to be making a video on it. What you can do is, once you define and you prove everything, the question could be, okay, so question. What if m does not belong to H2. So what if you don't have a martingale binding on H2? Well, there is a class, not in mathematical sense, of processes, stochastic process obviously, called, and again, I haven't really found much on this topic on YouTube, local martingales. So what's a local martingale? A local martingale is a continuous, and again, in the sense of its trajectories, and adapted process. Okay, means that if you, when you take, you have your probability, just a reminder, because I just watched a video of a professor talking about financial engineering and talking about the stochastic integral, and I haven't really remember what adapted means. So adapted means once you define your filter prob space, excuse my handwriting, but I'm going fast, it's filtration. It means that it's your process is FT measurable. Okay. So, yeah. So, okay, sorry, got lost for a minute. Continuous process such that for every the increasing sequence of stopping times, what you have is you get that, so let's call it L, continuous. The moment you stop the process, if once you stop it you get a martingale, so martingale. Okay. So what you get is, basically, the takeaway is, you can define the stochastic integral for local martingales, so a much weaker set of processes, okay? Because bounding L2 is it's a pretty strong claim. Here we're just saying we have a continuous adapted process such that when stopped, with respect to stopping time, creating sequence stopping time, we get a martingale. Okay. Then you can define integral. Let's use L. Stochastic integral. Why does it work? What you do is instead of L2M, you use L2. We called it log of M. So M now is no longer in H2. M is a continuous local martingale. Okay, so you just define L2M. What is that? That's a set of progressive processes again, such that now you have control over the integral. This integral, no longer its expectation. So, clearly, L2 log is in L2 M. Okay, and everything. So these properties 1 through 4 still hold true. The only difference is obviously here. You're gonna have no longer, you're not going to be in H2, but you're going to be in, you're going to have a continuous local martingale. So basically, bounded martingales, bounded in L2 against local martingale. Okay, so Here, the integral is in H2. Here, you have a local martingale. Now, okay, just let me finish and then I'll go through it. So getting excited. Some even more interesting remarks. You don't have the isometry, okay? So 2 doesn't hold. 3 holds, okay? 3 holds, so you have uniqueness, and then you can do this. However, here n is in H2, here same, but n is a local martingale again, and then 4 holds, okay? Just the same, because you only care about stopping. Now, the question you could ask is, okay, but how do we prove all of this? Okay, well, the trick is you define appropriate how to prove the stochastic integral for local martingales. Well, the trick is you define appropriate stopping times. Okay, so you define increasing sequences of stopping times. They need to be appropriate. So what I mean by appropriate is, for instance, when you have to prove that h dot m is a local martingale, okay, and what you know is that if m is bounded, then is also bounded in L2. So you have theory for bounded modification L2 is the moment you define Tn for every n, obviously, as the first time that 1 plus hs squared against the quadratic variation of m goes above a threshold n. So clearly, if it's not clear, you can prove it. Tn, the sequence Tn, is increased sequence of stopping times, and what this Tn allows you to do is to control the growth of what? Of both this, which, remember, h is an L2 lock. Okay, so that's the definition of being L2 lock. If this is bounded, if this is finite, then you have h and L2 lock. But look at how we're defining it. We're saying, okay, it's bounded. Remember, Tn is the first time it goes above n. So if let's call it L stop at Tn means potentially that this okay, because at time Tn, okay, we have just gone past n. So when you stop it, you are at n or below it. Okay, so it's the first time you actually go past n. I mean, you touch n, basically. Hope that makes sense. That's again part of stochastic processes when you work with stopping times. So once you do it, so you have a bound on this, and you have an increased sequence stopping time. So everything, the trick is you'd use your, Montague convergence theorems, and everything can pass everything to the limit by monetary convergence. So that's why measure theory, once again, is always important. So that's a trick, basically. And then, so this, for instance, was how you prove that the stochastic integral for local martingales is a local martingale, okay? And then, again, when, for instance, if you have to prove if you have to prove this, you also define, you basically need to define appropriate again, sequence of stopping times, okay? So we're at 30 minutes, and we just read in 2 pages, but I feel like I talked a lot, and I hopefully gave you a rough idea of what's behind the stochastic integral, even though I haven't really said much, but there's, again, could be talking for hours. But mathematically, that's what's going on behind it. So the idea is you define everything for binary martingales. You prove it. How do you prove it? Do we have time? So should I just give you a rough idea? So it's not really hard. So to prove one, you basically use definition of the elementary stochastic integral elementary processes. And obviously here what you need to prove that this is a martingale, it's continuous, and then the trickiest part is you need to prove that it's bounded in L2. So you need to prove that this is bounded. How do you prove it? You use, again, this definition. You plug in this in here of the expectation of a square. So you're gonna get 2 sums, one in I, let's say one in j, of hi, the increments, blah blah blah, hj. And what you do is I'm going too fast, am I? You condition everything on tj, and eventually you prove that what you're left with is just the quadratic variation. Do we prove it? I'm just giving you a lot of confusion, am I? So, yeah, who cares? So, 1. I'll just leave a timestamp for proof. I'll give you a rough idea, right? So we don't waste too much of your time. So, so the integral is a martingale. How do you prove it? I don't know. What you need to prove is that the product, the sum, you need to prove that the product so the difference of martingales is a martingale, right? Yes. The hardest part is proving that the product of a progressive process against a martingale is again a martingale. That's the hardest part. And then if you prove that all of this is a martingale, the sum of martingales is again a martingale. Okay? So the hardest part is proving that the product of these two is a martingale. Continuous, pretty obvious. Bounded. So you need to prove this is bounded. As I was saying, you use a definition okay, of the stochastic integral for elementary processes, because then again, remember, you can work by density. So if you prove it with elementary processes, you can eventually work by density, and eventually what you're going to be working with is that the sum of the expectations of xij. Remember the notation we talked about. These are the increments stopped against the increments for j stopped. And again, this is sum in I and j, right? So, and that's the partition up to the partition. Okay, makes sense? I'm writing this, Okay, this is nothing but this. Sorry, guys. This is an equal sign. Okay, right? If using the definition of elementary process. So you split it when I and j are equals. What you get is this. Squared plus twice when I is lesser than j. This. Now, what you do is you condition everything on tj. Okay, so this is not important because it's ftj measurable. You're assuming that, remember, I is smaller than j, right? So if you condition everything on tj, okay, so that's again the filtration tj. What you get is this I is smaller than j, ftj measurable, it goes out, ftj measurable, it goes out, ftj measurable, it goes out of the expectation, obviously, of the room. It leaves the room. So you get xi, hi, xj, the increments, the expectation. So now let's write it in full. That makes sense. So that's the increment. That's how you write it. Up to tj. Sorry, that's j. So, but m is a martingale. ftj measurable, and this is equal to mtj, right? So you get. So this is, don't let me write. Don't make me write it. This is equal to 0. So everything is 0. So what you're left with is this. But then you can prove. So now you start bounding. You can bound this with c, the increment squared. And you can prove that. Excuse me. You can prove that this is actually equal to when you I forgot the sum. This is actually equal to the difference between the last and the first squared. Okay, you can prove that, and that's 0 because we started in 0. Stopped, and m is in H2, so this is bounded by definition. So this is bounded. So what is bounded? Excuse my handwriting. This. So as a matter of fact, the stochastic integral is indeed in H2, right? Once you take this up. Okay, take the supremum everywhere, and it's bounded. If you take the supremum here, then the supremum goes here in time, and the supremum goes here, but this is bounded in L2, blah, blah, blah. Okay, that's formally how you should do it. Just then, so that covers 1. 2, you need to prove that these two norms are equal. These two norms are the norm in L2, as we discussed, is this. Against the quadratic variation. And the norm in H2 is this. The quadratic variation at infinity. So what you need to do is you need to prove they're equal. You start with this. Basically, once again, you use basically as 1, as 0.1, you show use the definition of a stochastic integral for elementary processes, and eventually what you need to prove is, so let me write it down. I'll just write down the highlights. So the idea is you write it down for elementary processes, and what you need to prove is so that would be, it's very nasty, that's hi mti plus 1 infim v minus mti infim v minus mtj I again infim u plus mti inf u. What? The sum over partitions. Okay, you can write that. These are the Riemann sums, and then xj. So that's the definition of the quadratic variation, right? If you remember. Do you remember that? So this would be the quadratic variation up to time t. We're not talking about the limit yet. We said in the first minutes. And everything is the same here. Okay? So that's the definition. What you need to prove is that every time I is different than j, so you can have I is more than j, I greater than j, and then you can prove obviously u and v can be, you need to show the cases basically. ti plus 1, tj plus 1, tj plus 1. You know, uv could be here, u and v, use red. It could be here, so in between. You show the cases, and basically you show that everything is 0, apart from when they're equal. And then when they're equal, eventually you can show that you do go to the excuse me. It goes to the, sorry, prove eventually that it goes here. Okay. But it's equal to this, okay? But what is this? That is actually is the definition for elementary processes of the L2 norm, okay? If you write H as an elementary process, you're left with this. So they're equal. But what we proved is, we proved two for elementary processes. Then you use density, and you get the claim. 3 is uniqueness. That is, it's not hard. You again use elementary processes. You use that, and then you need to show the limits when you pass through the limit. That's a bit more tricky, but it's the same reasoning, same argument. And then 4 is actually very simple. To prove 4, you use 3. You use uniqueness in 3, so you prove that. You prove this using 3. Okay, so use property 3, and by uniqueness you get everything you want. So, forgive me if I went too fast here on the proofs, but my what I wanted to show is the ideas behind how the stochastic integral is defined, and this is not, your regular, again, probably there's someone who did it better on YouTube. For sure there's someone who did it better in class because they have 20 years experience and they're a professor. But what I want to show is a deeper theory of stochastic integration for not usually you get your usual, your standard Brownian motion, but this, the Brownian motion clearly falls into this category, and clearly is going to continue a local martingale, because the Brownian motion is martingale. When you stop it, you start getting martingale, so you get a local martingale. Okay, you don't care about boundedness because you can work with boundedness without boundedness, as we showed, using appropriate sequence of stopping times. So that's what I wanted to show. If you have any questions, just let me know in the comments. Hope you find that useful. There'll be more because I need to give the exam, so I need to prove myself I know the things, and that's the best way to do it is try to explain it as they say. So thank you for watching, and yeah, I'll see you in the comments. Take care, guys. Best of luck if you're studying this in your exam.